Okay, good afternoon, everyone, and thanks to the organizers. So I'll be talking about fluctuating jets in planetary atmospheres. I think most of us are quite familiar with the banding patterns that are typically seen in Jupiter atmosphere. Here on the left-hand side of the image, I have the polar view of South Pole view of Jupiter, where these jet structures are clearly visible, and on the right half, we have the jets that are observed in laboratory experiments. Now, these jets are not only typical to Jupiter, many other planets like Saturn also have very strong jets. In fact, this can be realized also in Earth's atmosphere and Earth's ocean, but since the jet fluctuations are very high here, one has to do a monthly averaging to get a mean flow picture. And these fluctuations basically constitutes the basic motivation of this talk. So what determines the strength of the fluctuations? And is there any universal feature of these fluctuations? And what can they tell us about the underlying flow field? So I'll be giving you a spoiler here. So this R beta, this is a non-dimensional parameter, and this characterizes the strength of these jet fluctuations. If you look at the value here, for Jupiter, this is very high compared to Earth's atmosphere and oceans. 1.5 is the base value. So that's why for larger orbiter you get stronger jets, while for smaller orbiter you get highly fluctuating jets. This is from some laboratory experiment on a rotating water tank. Here also you can see these fluctuating jet structures, and this is from my numerical simulation. So next thing is, how do we model such flow features? So before telling you that, I should tell you what are the typical scales of motion here. So for Earth's atmosphere, it is around 1,000 kilometer, and for ocean, this is around 100 kilometer. Now, when we are looking at such large scale flows, because of the large aspect ratio, basically large horizontal breadth compared to small vertical depth. So because of that large aspect ratio, you can effectively consider these flows as two-dimensional, and on top of that, you have the rotation, which basically their Coriolis force act as linearizing the motion. So the minimal model will be 2D Navier-Stokes equation, and on top of that, this Coriolis force term here. Now, when you are interested at some, say, local motion around some latitude theta, then you can consider the that region as a plane, basically, and you expand the Coriolis parameter f here in a Taylor series expansion and truncate it at first order. And this gives the most celebrated beta plane approximation. Then you plug this into in place of this equation and take the curl of this equation and go to the usual stream function vorticity formalism. Then you can numerically simulate it and get these jet structures in the flow velocity field. Now, if you look at the flow vorticity field, some interesting pattern arises. So here you see these layered structures with sharp interfaces. Here I'll be characterizing these interfaces basically. Actually, the fluctuations that are here in the jet structures, those will be inherited by these interfaces. So characterizing those interfacial fluctuations will be goal of this talk. So before going into that, I should first tell you what the basic picture here. What determines the strength of these jets? This is a schematic of the energy spectrum. On the right-hand side, on the horizontal direction, I have the wave number, which is basically inverse of the length scale. Now, energy is injected at some length scale corresponding to kf. Now, in the usual 2D turbulence, we have the inverse cascade of energy. So small eddies will merge and create larger eddies, and energy will propagate upstairs. Now, if I did not have this have any rotation, then I would not have this region, and energy propagation would have stopped here, and then large scale dissipation would have taken place. But since I have rotation here, so what happens is that when the flow reaches at this scale, then waves start to interact with the eddies, and I won't talk in detail about the wave interaction part here, but what actually happens is that because of the wave interaction, these eddies will project onto jet structures here, and the flow field will be a mixture of both eddies and jets until it reaches this Rhine scale, another length scale. And after that, the flow field is dominated by these jet structures only. So the strength of these jets will be determined by the like width of this region. So larger width means eddy fluctuations will be diminished and jets will be much more stronger compared to when the width is small, then eddy fluctuations will be larger. So you can define a parameter, zonostropic parameter, which is basically the ratio of this scale by this scale. And zonostropic parameter high means stronger jets, like what happens in the case of Jupiter's atmosphere. And zonostropic parameter is lower means weaker jets, like what happens in Earth's atmosphere and terrestrial oceans. Now this is a simulation for three defined values of orbita. Here we'll see that as orbita increases, both the number of jet increases and the fluctuations will diminish, because here if you look at the interface itself, the fluctuations are quite small compared to the earlier case or smaller for smaller orbita case. What we'll be doing is characterizing these interfacial fluctuations. So first we have to track the interface then. So after several trial and error, we found that these interfaces will correspond to the velocity maximum of eastward jets. Eastward jets means these yellow jets, and these interfaces will correspond to the maximum of these yellow jets. And if you track those spatiotemporally, you get this. You get this contour, the spatiotemporal position of those contours. And then if you want to characterize it, you define a height field, which is basically the deviation of a contour from their mean profile. And then you do analysis on this height field itself. The first thing is, if you look at the space-time plot, these are also called chymograph plots, you see these tilted banding patterns. What these patterns mean is that the fluctuations are not localized. If you have a fluctuation at x is equal to x0, then later time it will propagate along the interface and go to some other position. And this can be explained using the wave-eddy interaction. Actually, Rossby wave elasticity and Rossby wave radiation stresses are responsible for this. And what they do is they couple or correlate the fluctuations, and in this way they can suppress the large amplitude excursion, which is also evident from the probability density function of the height field. Here you see a sub-Gaussian PDF, which basically means that the large amplitude fluctuations are kind of suppressed. Next thing is you look at the temporal statistics, like mean and variance along like in the time direction. So first you segment the contour into sectors. You look at any sector, then if you look at its time evolution, you will see these fluctuations. These are not random. There are specific structures in these fluctuations. If you look closely here, you will see that there is kind of smooth ramp compared to like a stiff jump, like we see in the shortest solution of Burger's equation. And in the variance, like a temporal evolution of sectoral variance, you see these intermittent structures which they decrease, the degree of intermittency decreases as the jets become stronger. Next, you can look at the frequency spectrum itself. And indeed, the mean spectrum shows like Burger's like scaling f to the power -2, whereas the sectoral variance, it shows different scaling regimes, mainly these two regimes, like we see in beta plane turbulence itself. Next thing is to ask how complex are these systems? So, is there any particular length scale associated with it, or there are like a range of scales? So to answer that, we borrow idea from 3D turbulence itself, like basically the multifactorial formalism of the dissipation field, turbulence kinetic energy dissipation field. I'll give a brief overview of it. So Kolmogorov predicted that the dissipation will happen on 3D structures which are uniform. But later, like wind tunnel experiment and numerical simulations also found that actually these are not exactly 3D-dimensional structures, rather they are like fractal subsets which are embedded in 3D, and each of those fractal subsets can be associated with the scaling exponent alpha. This alpha, this is the dissipation field. Kolmogorov told alpha is equal to 1. So as you increase the size of the ball of radius L, it would not change, like the mean value would not change, average dissipation would not have changed. But later, doing numerical simulations, people have found various scaling exponents, a range of scaling exponents. Here I will provide you the mechanism or the analysis part. Yeah. So suppose so when you have a signal like the height field here, you can break it into boxes of size L, and then you can vary L itself. Now, if you have uniform structure, you had uniform structures, then each box would have contained the same exact content, and then as you increase the length or so, the total, the sum would have increased by the proportional amount, like L to the power D, where D is the dimension. Now, if you have intermittent structures, then some boxes will be there where there is nothing, and some boxes there are many stuffs going on. So one can define partition function. This is a loose notion, calling it a partition function. But if we call this a partition function, which is basically the q power of the total content within each box, then they follow this scaling argument from probabilistic description. And then from there, if you do some little algebra, you can find the range of scaling exponents and the corresponding fractal dimension. So here in shade itself, this is the singularity spectra. Here we see that if there was like only a single scaling exponent which would have been dominant, then only f alpha would have peaked only at single alpha. But here we see a range of alpha values, which basically means that there are range of scaling exponents. Also, this is the correlation dimension, and we see that for positive q, these are almost flat. It means that large fluctuations are not that much dominant compared to the small fluctuations, which are this part, which basically contributes to this part mainly. So to conclude, jet fluctuations are spatiotemporally correlated, which can be obvious from the banding, tilted banding patterns in the height field. Also, the interfacial fluctuations, they exhibit like Barger's like Ramcliffe structures with f to the power -2 frequency spectrum. And secondly, why do we care about the strength of these jets? Because in this simulation, initially you had an uniform distribution of inertial particles, and as the flow evolves, you see that they organizes like around the jets itself. So this is very interesting and also applicable in the atmosphere, at least Earth's atmosphere, where the jet, atmospheric jet, which is surrounding the atmospheric Antarctic polar vortex, it basically determines the strength. Its strength basically determines how much like different gases, say ozone, will go into the pole, and it basically controls the ozone depletion rate itself. So this is an ongoing work. So thank you.
Sandip. Where you saw the scales of eddies and waves are present there. Can you go back? Yeah, this one. So you're forcing the eddies, right? Or
here, both this is the equation itself contains like this equation. It itself contains the this wave part. Like
waves and eddies both are present in the system. At the starting point, you have both eddies and waves. Both are there, right? Now,
then at some later point, this starts to dominate the picture.
Waves start to dominate the picture. Okay.
Yeah.
And then you'll have the full planetary atmospheric wave, right?
Yeah.
Okay. Okay, I don't know the reason exactly how this eddies after wave eddy interaction, how eddy is getting diminished. I couldn't understand that properly.
This is basically the mechanism is same like similar to like internal wave mixing kind of. So there also like this potential vorticity mixing happens, right? Wave, because of wave eddy interactions. Initially, potential vorticity like would have been linear, like if so potential vorticity is defined as like omega flow vorticity plus this beta y term.
Yeah.
So initially, if you have random like eddies, so omega is like uniform. So then this potential vorticity will go as this along a straight line. Now, as the flow evolves, as the wave enters into the picture, there will be gradient formation will happen. Like this picture will go like this kind of picture.
Yeah,
Will
yeah.
be there.
It will be wavy kind of, but eddy will not get diminished. Like,
No, that's what now it does not stop there. And whenever this kind of formation happens, now where the most of the mixing is happening, this is a positive feedback mechanism. Now, where most of the mixing happening, there it gets much more again mixed. Like if there is some mixing in some region or in some place, much more mixing will happen there. And in other places, the waves will contract, or waves will accumulate there. So if you look at the potential vorticity contours itself, like along the jets, there will be this. These are the potential vorticity contours. Then there will be mixed region. Then there will be again potential vorticity contours. So it does not stop until the jets become jets have more energy than the any available eddy itself. People have done any experiments like put in an eddy field and like which has energy greater than jets, and you will see after evolution jets will have more energy and eddy will have lesser energy.
okay, thanks.
Hi, I had a couple of questions. The first one is, when you showed the beta effects, what's the relative strength of your F naught and beta?
If not, really doesn't matter because you are going to the vorticity formalism. There, if you take a curl, this is a constant thing. Like F naught is basically at what latitude you are working on. So,
But it will come in the potential vorticity, right?
F naught.
Yeah.
F naught doesn't. No. No,
Right.
F naught doesn't come into potential vorticity.
It's,
If you don't go into this beta plane approximation, that total F will be there.
Right.
But
right.
not when after you go to this approximation, this does not come.
But-
F0 is a constant part.
But F0 is multiplied with U. So when you take a curl, there will be a curl of F0 cross U, right? That term you're saying in 2D goes away?
Yeah, ultimately it goes.
Okay. Maybe we can talk about that
Yeah.
later. The second question is, have you checked these fluctuations in a rotating shallow water model, for example? Because usually large aspect ratios are modeled with rotating shallow water models.
Yeah. This is first of all simpler and more studied. That's why we did it. Then second thing is when you go into the the fluctuations are there also. But I have not done any calculation or any analysis on top of that.
Right.
But in particle, when people do particle stuff, they generally do the shallow water or double layer model.
Right. That's all. Thank you.